Hi, my name is Professor James. Welcome to this journey through space. Today we are going to study the chapter, which is Aerodynamics-Driven Design Thinking. In this chapter, we'll explore how aerodynamics and computational tools play a pivotal role in modern aerospace design by enabling engineers to optimize aircraft components for performance and efficiency. Design thinking in aerospace involves an iterative approach to refinement, integrating aerodynamic performance with structural integrity and manufacturability. Let's dive into how simulation-driven design, multidisciplinary optimization, and real-world constraints shape the future of aerospace engineering. Fundamentals of aerodynamics-driven design thinking. Aerodynamics-driven design thinking emphasizes the integration of fluid dynamics and structural considerations throughout the design process. The iterative design process replaces traditional linear design with continuous cycles of simulation, evaluation, and optimization. Multidisciplinary design optimization, MDO, takes into account various interacting factors like aerodynamics, structures, propulsion, and controls, creating a unified optimization problem with multiple objectives. Design is refined and optimized based on feedback from simulations, helping engineers to balance performance and weight reduction while meeting structural and regulatory constraints. The key to modern aerospace design is the ability to test and improve designs virtually through computational tools like CFD and FEA, rather than relying on physical testing alone. This approach leads to faster prototyping and lower development costs, ultimately resulting in safer and more efficient aircraft designs. The iterative process in aerospace design. The iterative process is central to aerospace design, where designs evolve through continuous feedback loops. The process begins with an initial concept that meets basic requirements for performance and aerodynamic efficiency. CFD simulations are run to evaluate the aerodynamic properties, such as lift, drag, and pressure distributions, to refine the design further. Structural analysis is performed using FEA to ensure the design meets strength and rigidity requirements under operational loads. After each simulation, the design is refined based on evaluation criteria, ensuring that the structure performs efficiently in both aerodynamics and structural integrity. The iterative process continues until the design reaches an optimal balance, achieving the required performance while meeting all safety and regulatory constraints. Multidisciplinary Design Optimization, MDO. MDO is a key methodology that integrates multiple engineering disciplines into a unified optimization framework. MDO simultaneously considers aerodynamics, structures, propulsion, and control systems to achieve optimal design solutions. The design problem is formulated mathematically with an objective function, e.g., minimizing drag, and constraints, e.g., structural safety and performance requirements. MDO allows for the coherent exploitation of interacting phenomena, helping to balance weight reduction, fuel efficiency, and structural strength in aerospace designs. The methodology also includes trade-offs, such as the weight versus performance balance, where lightweight designs improve fuel efficiency but might compromise structural safety. The integration of different engineering disciplines ensures that the design process is holistic, addressing all facets of aerospace performance simultaneously. Design constraints in aerospace. Design constraints are the real-world limitations that must be considered when optimizing aerospace components. Geometric constraints include airport compatibility, manufacturing limits, and ground clearance, ensuring that the design can be manufactured and operated within practical limits. Performance constraints like takeoff, landing distances, climb rates, and range requirements ensure that the aircraft performs as expected under various flight conditions. Regulatory constraints, such as certification standards, noise regulations, and emissions limits, dictate the permissible operational characteristics of the aircraft. Manufacturing constraints include production costs, material availability, and assembly feasibility, which limit the cost-effectiveness and practicality of the design. By using simulation-driven design, Engineers can test different configurations and find solutions that meet all these constraints while achieving optimal performance. Weight versus performance trade-offs. A key challenge in aerospace design is balancing weight reduction with performance enhancement. Weight reduction is critical because every kilogram saved can increase the aircraft's range by approximately 15 kilometers. However, excessive weight reduction can compromise structural integrity. On the other hand, performance enhancements, such as larger engines or advanced aerodynamic features, often lead to an increase in weight. For example, a larger engine may provide more thrust, but also add significant mass. Computational resolution in design allows engineers to find the sweet spot between low weight and high performance, using simulation-based exploration of the design space. Pareto frontiers identify the optimal trade-off solutions between competing objectives, enabling engineers to make data-driven decisions. By exploring these trade-offs through iterative simulations, engineers can identify solutions that maximize the overall performance while minimizing weight and ensuring structural integrity. CFD and FEA coupling for robust design. Coupling CFD, computational fluid dynamics, and FEA, finite element analysis, is essential for designing robust aerospace structures. Fluid structure interaction, FSI simulations, capture the critical interplay between aerodynamic forces and structural deformations. For example, wing deflection due to aerodynamic loads can significantly affect the aircraft's performance. CFD calculates the pressure distribution on the surface of the structure, while FEA determines the resulting structural deformations and stress distribution. The deformed structure alters the airflow, which in turn affects the aerodynamic performance, creating a feedback loop that must be resolved iteratively. Two-way coupling between CFD and FEA provides a more accurate simulation, as both systems exchange information until the solution converges to a stable state. Data-driven decision-making in aerospace. Modern aerospace design is increasingly driven by data analytics to optimize performance and efficiency. Big data in aerospace comes from the vast amounts of simulation results generated by tools like CFD and FEA. These data sets are analyzed to extract meaningful patterns and insights. Machine learning techniques are used to identify non-obvious relationships between design parameters and performance metrics, helping engineers make better-informed design decisions. Uncertainty quantification methods determine the confidence levels of simulation predictions, providing a statistical basis for design decisions. Data-driven approaches also enable real-time design optimization, allowing engineers to explore the design space more efficiently and identify optimal solutions faster. These techniques not only speed up the design process, but also lead to more reliable and robust designs that perform well under various operational conditions. Parametric studies and design of experiments. Parametric studies and design of experiments, ADUE, are essential for exploring multiple design variations efficiently. Design of experiments is a structured approach to vary multiple parameters simultaneously and systematically, ensuring comprehensive coverage of the design space. Full factorial designs test all combinations of parameters, while fractional factorial designs reduce the number of experiments, saving computational resources. Latin hypercube sampling, LHS, ensures that the parameter space is sampled evenly, providing a statistically balanced set of design points with minimal computational cost. Adaptive sampling focuses on the regions of the design space that are likely to yield the best results, accelerating the optimization process. These methods enable engineers to efficiently explore design alternatives and identify optimal solutions for complex aerospace systems.